بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله. In this video we will start discussing the control systems. Okay, chapter 10 is about the time domain analysis of control systems. So keep in your mind, when we discuss the controller or control systems in this chapter, we are talking about, or we are trying to control the transient response of dynamic systems. The transient response of dynamic systems. Okay, keep this in your mind. Okay, so the objective of this chapter, the basic concepts for classic controls. The basic concepts of classic controls. This is the first chance for you to understand the control systems, how they work. Okay, how to design the controller. This is our first chance in this chapter to design the controller for the transient response. When we say transient response, we're talking about the stability, the accuracy, and the speed of the response. We will talk about this, inshallah, later. So today, we're going to talk about the feature of control systems. This is the topic of today's lecture. Okay, we will talk about what type of controllers that you see around. Okay, then we will focus on designing the controller for the stability only. Okay, using these three methods. Inshallah, we will talk about it later lectures. Okay, so let's start. All right. Now, as a control engineer, let me show you something. As a control engineer, we usually start from the block diagram. What is a block diagram? I want you to pause this video and go back to chapter 4.2 specifically. There you will see a video, okay, showing you the basics and the fundamentals of block diagrams. Okay, block diagram is the graphical representation of the transfer function of your system. Okay, so usually as a control engineer, you start from the block diagram. This block diagram, for example, representing a control system. Okay, here is the input, we call the reference input. Here is the output. This is the feed forward. This is the feedback. This is the error signal. Okay, this is summing point. So please go back, refresh your memory in chapter 4.2 about the block diagrams, because this is where we're gonna start really working on designing the controller from the block diagram. Okay, all right. So before we start from here, okay, I want to show you an example, the fundamental or the physics of the controller. Usually control engineers start from or work on mathematics, right? From the block diagram, everything mathematics. But physically, what does it mean, a controller? Physically, just like the dynamic systems, physically it means many things. There are fluid systems, they have different type of physical type of controller. Electrical systems, the physics of the controller look different. Okay, mechanical systems. But once you reach the transfer function, okay, all the methods for designing the controller will be the same. All the types of controllers mathematically are the same. Okay, I will show you what are the types of controllers that you see in any control system. So we will pick an example here, a fluid tank system. Okay, and I will show you physically what's a controller. Okay, then we will move to the mathematics, the block diagram, and from there we will start talking about designing the controller. Okay, all right. Remember this example from chapter 7. Okay, this is a fluid system. Okay, it's a steady state system with a small fluctuation around the steady state. So the system starts, the dynamic system starts when we add a small fluctuation around the steady state flow in, and I will call it small qi. So small qi is my input in this system, and the output is the small h, the deviation in the head inside the tank. All right, we derived the transfer function in chapter 7, so we don't have to do it again, but to refresh your memory, these are the equation of motion and the transfer function that we derive. This is the transfer function when the input is small qi and the output is small h. Okay, we got it R over RCS plus 1. R the resistance, C is the capacity, S the complex variable. So this is the transfer function of your system. Clearly, it's a first order system, right? All right. All right. Now, we have a problem here. If I tell you, can we control H? Do we have a control over H? And for example, how do I control H if I want H to be exactly 1 meter inside the tank? For example, can we control it? Which value you will pick for QI? You don't know. You have no control, right? If your QI is step function, you have no control over H. So we want to have control over H. I want to have a specific H, the head inside the tank. I want it specifically to be, for example, 1 meter. So what I'm going to do physically, I'm going to control or actuate the valve, right? Open it or close it. So how are you going to do this? Now we will introduce a new reference input. We will call it a new input. We will call it reference input. Okay. So this input, I will call it small x. Okay. After the small deviation. What is this input? This input will be connected to a sensor to measure exactly how much the head inside the tank. Okay. And this input also will be connected to an actuator, which is the controller, that will control or actuate. We call it actuation, by the way. Any action from the controller, we call it actuation. It will actuate the valve, open it or close it. Okay. So our job is to design this controller, how much exactly we want to open or close the valve in order to maintain exactly our real or expected value X for the head. So X is what I want exactly. H is what actually there. Okay. So from here we will start designing the controller. All right. Now we will pick the simplest types of controllers. We call it K. So K is an integer. We call it the gain or the proportional controller. Usually it's a positive value, positive integer like 0, 1, 2, 3, 4, 5. Okay. So this is the simplest types of controller and most common, most popular. It's similar to the volume in your radio, in the car radio, for example. You see the volume 0, 1, 2, 3. This is similar to the gain here that you see. All right. Now, what is this controller will do? It will use the error between the real head inside the tank, this one, and its expected value. So expected value, what I want, minus what actually there. Okay. We call it the error. So the proportional controller will use this error in order to actuate the valve, the QI, open it or close it, right? So mathematically, K is multiplied by the error, okay? K times the error, X minus H, okay? To actuate the flow in. How it works, I will give you an example. If I want the head inside the tank to be exactly 1 meter, okay? So the controller, the system will start at t equal to 0. It will start to pour in water, for example, or fluid inside the tank. After some time, you measure the head using the sensor, the feedback we call it. And the head was 0.5. So 1 minus 0.5 is 0.5. Now you need always to pick one value or stable value or constant value for K. For example, I will use K here to design K for 1, only 1. Okay, number 1. So after a while, you measure it, it's 0.5 H. 1 minus 0.5 is 0.5 times K, which is 1. It is 0.5. So QI will be 0.5. What does it mean 0.5? It will pour more fluid, like 0.5, okay, into the tank. Now, after some time, you measure the head inside the tank, and it was 1. Okay. Your expected value always will be 1. You don't change this one. Okay. This is what will change after a while. Okay. So 1 minus 1 will be 0. And K is already 1. So 0 times 1, it will be 0, which will tell the equation, this equation will become 0. So the controller will actuate the valve and make QI equal to 0. That means it will close it. It means it will close it. So no more fluid into the tank, and then everything is under control. Now H is exactly what you expect, and then the system will stop, right? You reach your goal or objective. All right. This is simply how it works. Okay, physically how it works. Okay, just for your information, for this specific example for the fluid system. All right. Now our job is to start from here. How to build this block diagram? Usually, as a control engineer, okay, you start from here, okay, building your block diagram. And usually, for this basic course, usually the block diagram is given for you, and you want to design the controller. Okay, so how did we come up with this block diagram? This block diagram represent this system, the control system. All right. This is the reference input, X, what I want. This is the actual output, the real head inside the tank. This is the feed forward. Here where you see the transfer function of the controller and the transfer function of the system, of the tank before adding the controller. And this is the feedback, the sensor, okay, which is usually equal to 1 because you want to measure exactly how much the output and compare it to the input. So this signal will be the error. How did we come up with this one for understanding? We want to understand how did we come with this block diagram. I will show you step by step, okay? Briefly. Okay. I will start from here, from this equation, okay? The Qi equal to K times the error, okay? The proportional controller times the error. So I will start from here, okay? Then I will take the Laplace transform, the Laplace transform. So Qi will be equal to K, the proportional controller, times the error in the Laplace domain. Remember, the error is X minus H, huh? Keep this in your mind. Then I'm gonna divide both sides by H. Okay. Then I'm gonna flip both sides, so H on the top now. Okay. Now, my objective is to have a direct relationship between X and H. Between X and H. This is my objective. I want to find the transfer function relating X to H. So how do I come up with this? I will start from here, as I told you. So what are the variables here? We have H, we have Q, we have H, we have E. Okay, what is E? E is X minus H. Okay, so now when this error means we have X minus H, that's cool. But we have a problem. We want to eliminate this function. We want to have direct relationship between H and X directly. So how to come to this? Remember, H over Qi is equal to R from RCS plus 1. What's this transfer function? This is the transfer function of the original system before adding the controller. Remember this one? So we're going to use it here. Okay. So I'm going to substitute, instead of this one, I'm going to substitute the transfer function here in order to eliminate Qi. So H over Ke, where is it? H over Ke will be equal to R over RCS plus 1. Okay, so I'm going to take K, or sorry, I will take K to the other side, just like I did here. Okay, from here, it's already shown here. H over Qi equal to this one, R over CS, which is equal to this one. So I'm going to take K to the other side. Okay, and the error is H minus K. Now we eliminated Q, that's good. Now what are the only functions that you see in this equation? I see only H and X, excellent. K is a constant, controller. RC also constant. S, complex variable. So what you're going to do here, you're going to collect all the coefficients of H together on one side and all the coefficients of X together on the other side, just like we did in chapter 4, okay, in order to get this equation, this transfer function, okay, which is going to be KR over RCS plus 1 plus KR. What is this function? This function relating H directly to X. The input here is X and the output is H. So this function, if you want to show it in a block diagram, this is what you're going to get here in this function. Again, you need to review chapter 4 to understand what I'm doing here. KR, capital K, over RCS plus 1 plus K R. Okay, what's the input here? X. The output is H. Okay, nice. But this is the CLTF, by the way. We call this CLTF, the closed loop transfer function. Okay, I want to start or build this feedback control system. We call this feedback control system, negative feedback. Okay, so how to go from here? This one, the error signal. This one, the error signal. This is the error. Okay, which is E. Okay, which is this one. Where is the error? This one. Right? Where is it? Yes, here. This is the error signal. But I want to have, yes, this one, nice one. This is the one we're looking at. So here the input is the error, output is H, right? This is N, this is N, okay? This is out. So this one here will be the input, right? Input, and this is the output H. So in between you must have KR over RCS plus 1. Is it KR over? Yes, good. So we started from here, from the error, and the output is H, and the feedback will be equal to 1 usually. Why? Because we want to measure exactly how much the output, sensing how much the output, and subtract it, this is a negative sign, from X. So this the error is X minus H, right? True? So this must be representing the control system. Now, how to prove this, if this is correct? You can do this, the following, okay? H over X, okay? We call this the CLTF. It will be G over 1 plus GH. What is G? G. Everything on the top here, we call it the feed forward transfer function, G. Everything on the back, we call it H. This H is not, I'm talking, not the head, okay? This is not the head. This is different, huh? This is H. We usually call the feedback H. And we usually call the feed forward G. Just like a default, okay? So this is how we get the, how did we come up with this one, the CLTF? Go back to chapter 4, okay? 4.2, you will see the video. How did we come up? It's already proven, okay? It's all algebra. So you can prove this. Put G, which is equal to KR over RCS plus 1. By the way, you don't have to do this now. This is just for understanding, okay? I want to prove to you how did we come up with this one. Plus, or 1 plus G, again, KR, RCS plus 1 times H, which is 1. If you derive this function, okay, or equation, if you derive it, okay, you must get what? You must get this one. It will be the same, okay? I don't want to waste your time, but you can do it, and you should get the same. That means what? This is proven to be correct. All right? All right. This is for understanding, okay? Now, we really need to understand what is the going on inside this block diagram. This is what's really important, okay? This is what's really important. Look, I will separate this K here and the rest here. Because the equivalent of 2 blocks in series, what is the equivalent of 2 blocks in series? The multiplication, right? How do I come with this one? Go back to chapter 4, okay? In the video in chapter 4.2, these are the fundamentals of block diagrams, okay? This is H, okay? This is a typo, H. All right? Now, see, this K is what? K is the proportional controller. What is this R over RCS? Did we see this before? We call it the plant. What do I mean by plant? The plant is the transfer function of the original system before adding controller. The plant is the transfer function of the system before adding controller. The plant, we don't change the plant. The plant cannot be changed. It's fixed. What can you change? K, or the controller. This is what you design. This is cannot be changed. What you change as a control engineer or design is the controller. This is what you change. 0, 1, 2, 3, 4. How we change it? Up to your needs. What are the needs? There are different needs. Are you talking about transient response? Yes, in this chapter we're talking about transient response. For transient response, we're talking about stability. We're talking about accuracy. We're talking about speed of the response. Cool. Okay, these are the criteria that we want to design. How are we going to design the controller? There are many methods. What are the methods? Either we go to the characteristic equation, or we use Roth criteria, or we use root locus, and this is what we're going to focus in this course, inshallah, in this chapter. Okay, this is briefly how we design the controller. Okay, all right, cool. Now, this is the control system, the block diagram for any control system. Any control system, okay, can be represented in this block diagram. We always start from the reference input. Reference input is what you want, your expectation from the system, how much you want. Okay, we usually end at the output, the real output. How much did you get? Okay, what we call all the transfer function on the top, we call it the feed forward transfer function. Okay, we start with the controller, some kind of controller. For example, here amplifier is like a proportional controller, and we end at the plant. This is the plant we want to control, the system we want to control, the actual system. And in between the plant and the controller, there is the actuator. So the actuator is like the media, okay, or the medium between the amplifier and the plant, okay. And this signal always will be the error signal. Why this is always the error signal? Because look, this signal is equal to how much? Equal plus the reference input minus the actual output from the sensor. Okay, so this sensor will measure how much exactly the output in order to measure the error. Okay, so we always start from the error signal. All right. And the sensor usually equal to 1 in most systems. Why it's equal to 1? Because this one will be multiplied by the output. Okay, so we want to measure exactly how much the output. So you multiply it by 1. Okay, so this is actually number 1, but we don't show it number 1. This is a transfer function. This is a transfer function equal to 1. Okay, number 1. But we don't show it because this is the default. Here, number 1. This is the default. If you multiply by any number, it will not change. So we usually use h equal to 1 in order to measure exactly how much the error. Okay. All right. And most of systems, the controller, you start with some kind of controller here to control the plant. And usually, most of the systems, the actuator is number 1. Okay. But not all of them. Okay. But usually number 1. Because you have direct control on the plant. All right. All right. But the actuator in mechanical systems, for example, if you have a robot, the actuator is the arm. The arm, usually the actuator. So it's the medium between what you want to, for example, let me show you. For example, if you have a robot, okay, if you have a robot that will pick some object on the belt, okay, like a ball. So this is the actuator. This is the controller, usually the controller here. Okay, and this is your system or the plant. You want to elevate the plant, you want to elevate the ball. Okay, so this is the actuator. For example, this is just an example, okay? What do I mean by actuator physically? Mathematically, this is the transfer function, okay? Which is usually equal to 1. All right, very well. All right, now let's review what we studied so far, or what we learned so far. Okay, this is the block diagram for a typical control system. We call it negative feedback control system. This is the reference input. This is the output. Everything on the top, all the transfer function on the top, we call it feed forward transfer function. Everything on the back, we call it the feedback transfer function. Okay. And the feed forward, usually we start with the controller in order to control the plant. This is the transfer function of the plant. The plant is usually your original system before adding the controller. Okay, the feedback usually equal to 1. Why? Because we want to measure exactly how much the output. Why? Because we want to measure exactly how much the error between the input and the output. Okay, so this is what we learned so far. All right, OLTF. Now this is important. What do I mean by OLTF? Open loop transfer function. If you open this loop, okay, if you open this loop, for example, if you open it, no more, okay, if you open the loop, so you'll have here the G controller, and this is the G plant. Okay, so this is X. All right. So no more, you don't need a summing point because there is nothing here, no feedback. If you open the loop, okay, and this is H. So you just open this wire, like imagine this is like a wire and you took it to the other side. All right. If you open the loop, how much the OLTF, the open loop transfer function, it's going to be GC times G plant times H, or G, if you call this G, the feed forward, G times H. So G times H, we call it OLTF. All right, this is what do I mean by OLTF. We need to remember this, okay? These are the basics of control systems. CLTF. What is CLTF? CLTF is what is the equivalent block diagram of this closed loop block diagram. CLTF is how much is the equivalent block diagram. Equivalent, so it's going to be how much? It's going to be G over 1 plus GH. Do you remember how did you get this? Yes? In other words, this is going to be X, and you want to find a single block diagram between X and C, for example, here. So it's going to be G over 1 plus GH. We call this what? We call it CLTF. Okay? Remember this. These are the basics. Okay? These are the basics. All right. All right. Okay. Now remember in the CLTF, G over 1 plus GH, in the previous example, in this one, this is CLTF, okay? This is CLTF, right? Where do you see the controller? We see the controller both in the numerator and the denominator. What do we call this denominator? This denominator is your characteristic equation. So do you remember what is the characteristic equation? The root of the characteristic equation will determine the stability of the system. We will talk about it, inshallah, next. Okay. So do you see the controller in the characteristic equation? The answer is yes. What does it mean? That means it's going to be part of the root of the characteristic equation. So what does that mean? That means it will control it, or it will have a direct control on the stability of the system. And this is the objective of this chapter. Okay, this is the objectives of this chapter. So the gain, K, the controller, will determine the performance of the control system, especially the stability. How do we know this? By looking at the transfer function of the CLTF. Okay, because CLTF is actually the equivalent block diagram of your control systems. All right. All right. Now, what types of controllers do you see anywhere? There are always 4 types of controllers. Okay. P, most simple. Okay. And the most popular, proportional controller, gain. It's a gain. It's a positive, or usually positive integer, 0, 1, 2, 3, 4, 5. Okay. This is most popular. PI, also popular. It's a proportional plus integrator. What do I mean by integrator? 1 over S. 1 over S is in fact the Laplace transform of an integral. Okay, that's why we call it integrator. So proportional plus integrator with some kind of gain Usually in the field, in the lab, you will have separate gain. One gain for the proportional controller and one gain separate for the integrator. Okay? This is what you see in the lab. So if you go to the lab, okay, you will see the controller usually. Let me write it here. The controller in the lab usually is a board like this one. Okay. In this board, you will have a button, for example, for the proportional controller, and another button for the PI, okay, or the integrator separately. So, and another button, for example, for this one, the derivative. Okay, derivative, we call it, integrator. So this one has a KP, and this one has a different KI, and this one has a different gain KD. This is in the lab. Huh? So in the lab, you can use either the proportional controller alone, or you can add an integrator, we call it PI, okay, which one has a separate. This is like the volume, huh? Similar to the volume in your radio, huh? Similar to the volume, where you can choose. It's like 0, 1, 2, 3, 4, huh? Depends. Same thing here, all right? So in the lab, usually in the lab, you will have separate gain for the integrator. And in design, when we use the root locus, you'll see next, when we design the controller mathematically, okay, we use a common gain. You use a common gain, okay, all right? So in this case, you will have one pool at the origin. We call this pool at the origin, the integrator. And we will have a first order zero. You need to remember this, okay? Because these are the basics of the controllers. Okay. Also, another type of controllers, but less popular, PD, proportional plus derivative. See, this derivative is the Laplace transform of a differential. Okay, you can use in the lab manually separate gain for each, or in the design for the root locus, we will use one gain, common gain, and it will have only a first order zero. We call it first order zero. All right. PID controller also popular, but this is the most complicated because it has a proportional, it has a derivative, and it has an integrator. Okay. In this case, you will have two first order zeros and one pole at the origin. Okay. One pole at the origin. As we proceed in this chapter, inshallah, it will become much more much more easier, maybe, if I may say, and it will be more understanding. Okay. All right. What are the major concerns when you design controller? Okay. This is going to be the last topic that we're going to discuss in this video. What are the major concerns when you want to design the controller? We talked about this briefly before. Now, let me recall it again. When you want to design your controller for the transient response, we focus on three things: stability, accuracy, speed of the response. Okay? Stability, when I say stability, for example, let me pick a second order system, okay? Okay, where is the transient response and where is the steady state response? This is the time response. This is a function, x of t. So, where is the transient response? This is the, clearly, transient response, right? And this is the steady state, right? All right. Stability, what does it mean, stability? Stability means, does this value go to a certain, does this response go to a certain value and stay within a range of 2%, for example? In other words, in mathematics, is this function converging or diverging? It's converging, right? Because it's going to a certain value, staying within this certain value. So this is stable system. This one is stable. Okay, or in math we call it converging, huh? So this is the major concern and most important concern in this, especially in this course. We will focus on the stability. We want to have always a stable system. How we reach this? We will use the controller. Okay. Number 2, accuracy. What is accuracy? The accuracy is the error. Okay, the error. For example, here we have the input. This is the output, right? The input, for example, is for example, here is a step function. Let me use another color. Okay, this is the input. Step function. This is the input. This is the output, okay? So the error is equal to input minus output. So if I tell you by looking at this response, time response, or transient, how much the error here? The error clearly is 0. Why? Because at the steady state, okay, there is no difference between the input and the output, so it will become 0. So accuracy is also a major concern when we design the controller, okay? Number 3, speed of the response. What does it mean, speed of the response? The settling time. The settling time, okay? Where is the settling time, for example, here? Here, this one. Okay, when it reaches, this is TS. How much time it takes to reach and stay within 2% of the final value? We call this speed of the response. Okay, so these are the 3 major concerns. In the lab, you will have more time, so we're going to talk about the error in the lab, how to design the controller in the lab. But here in this chapter, we will focus only on stability. Okay, all right. So we're going to discuss the stability. For the stability, we will use the 3 methods. Method number 1, by going directly to the characteristic equation and try to control the roots of the characteristic equation. Method number 2, Roth criteria. We'll talk about it later. And method number 3, this is the most common and popular method in control, which is the root locus. Okay? This is what we're going to focus in this chapter, inshallah. So thank you, and we will see you, inshallah, in the next lecture.